Okay, this is part 1 of the basic computing concepts from my series that I promised you all free of charge, covering hacking, cybersecurity, ethical hacking, penetration testing, wireless penetration testing, and so on.
What?
You can follow whatever path you want, but with these concepts, you're free to decide which direction you want to go. I'll make a clip for my Instagram. I'll post a video of at most 1 minute. The continuation of this video will be on YouTube or TikTok, actually on YouTube and TikTok. Okay, if you haven't visited my site yet, everything I talk about here will be at zerosday.com. Zerosday.com. Everything I cover here will be on the site. This entire roadmap I created will be on the site. If you're not subscribed, go ahead and subscribe. If you're not following the Instagram page, follow it. If you want to make a donation to keep our site going, our free platform with over 10,000 pages, click the Linktree button on Instagram or visit the site where you'll find a link on the home page for you to donate any amount. It's not a scam, it's not a fraud. I'm not trying to clone your card. Quite the opposite. There's a platform called Stripe, which is the largest payment platform in the world, and it's what manages these payments. All right, grab your notes, start writing things down, share the video, like it if you liked it, and let's go. So the objectives of this video are to understand the fundamental concept of binary logic and its role in digital computing, to explain the main functions of a central processing unit, the CPU, and its interaction with other components, to describe the differences and purposes of RAM and persistent storage, to trace the basic execution flow of a simple program from loading to completion, and I ask that you appreciate the fundamental building blocks that underpin all of modern computing and cybersecurity. At its core, a computer is a machine designed to manipulate information. To understand how it does this, we first need to understand the most fundamental language it speaks, which is binary. How does binary logic work, and what is the world of binary logic? All information processed by a computer, from your favorite music to the most complex lines of code, is ultimately represented as a sequence of bits. A bit, short for binary digit, is the smallest unit of data and can exist in one of two states, the 0 state and the 1 state. Think of it like a light switch. A light switch is either off or it's on. Off is 0 and on is 1. Simple. Even a chimpanzee would get that. So why binary? Because electronic circuits are inherently well suited to represent these two distinct states. A transistor, the fundamental building block of modern electronics, can either be conducting electricity, represented by the digit 1, or non-conducting, representing 0. This simplicity and reliability make binary the perfect choice for digital computing. These bits are grouped into larger units naturally. The most common grouping is the byte. So we have the bit and the byte. A byte has 8 bits. Almost forgot a finger there. 1 byte, 8 bits. So a byte has 8 characters, or 8 electrical signals, zeros or ones. When I type a character on the keyboard, it very quickly computes 8 bits. These binary values are grouped together to represent not just numbers, but also characters through encoding schemes like ASCII or Unicode, which are instructions for the computer and, in fact, all forms of data that exist in the world. We'll talk about encoding later on. This is super important for understanding cybersecurity, for pen testing, for hacking, for ethical hacking, for non-ethical hacking, for working with anything. You need to understand encoding. These bits are grouped into larger units. The most common grouping is the byte, as I mentioned, which consists of 8 bits. A byte can represent 2 to the power of 8, which is 256 different values. For example, using 8 bits, we can represent numbers from 0 to 255, where 0 is 0, 0, 0, and 255 is 1, 11, and so on. I must have missed a 1 in there somewhere. These binary values are used to represent not just numbers, but also characters through encoding schemes. Have you heard of ASCII? Have you heard of Unicode? That's encoding. Each computer, each region has a different encoding, but a file from one region can also have a different encoding. We'll get into that later. Now, the central processing unit, the CPU, which is the brain of the operation, is the component responsible for executing instructions. It's often called the brain of the computer because it performs all calculations, logical operations, and control functions. The main function of the CPU involves a continuous cycle known as the fetch, decode, execute cycle. The fetch: the CPU retrieves an instruction from memory. Decode: the CPU interprets the instruction to understand what operation needs to be performed. and what data to retrieve. And execute, the CPU carries out the operation specified by the instruction. This can involve arithmetic, which includes addition, subtraction, logic, comparisons, data movement, or controlling other parts of the computer. This cycle repeats millions or billions of times per second, allowing the computer to perform complex tasks. The speed at which this cycle completes is measured in hertz, with modern CPUs operating at gigahertz speeds, meaning billions of cycles per second. This term hertz is something you need to remember. It's very important. In fact, Hertz is the name of the guy who created all of this electronic framework. Hertz created many things, and I'll explain that further along. There will be a basic electronics course coming up later, but for now, understand that Hertz is a very important figure, and his name also became a unit to measure cycles. For example, the light bulb in your home.
Now let's talk about memory and the workspace for the CPU. For the CPU to execute instructions and process data, it needs a place to access them. Quickly, of course. I can't be accessing a hard drive all the time because it's extremely slow and costly. For the CPU to execute those instructions quickly, that's where RAM comes in. RAM is volatile, meaning it loses its contents when the memory or when the power is turned off. However, it's extremely fast, allowing the CPU to read and write to it with minimal delay. Think of RAM as the CPU's workbench. When you open a program, its instructions and the data it's working with are loaded from persistent storage into memory. The CPU then accesses that information to carry out its tasks. The amount of RAM a computer has directly impacts its ability to multitask and handle large programs. In other words, more RAM means the CPU can keep more information readily available, reducing the need to fetch data from slower storage. We have hard drives, right, when talking about long-term storage, and we have solid-state drives. Even though people think hard drives are extremely outdated and old, they're actually still being used. And we have solid-state drives, newer and faster storage devices that use flash memory, similar to a USB drive. So now I'm going to walk you through the flow of a program's journey. Understanding how a program moves through a computer is crucial for cybersecurity. Every program, no matter how simple, follows an execution flow. It goes through loading, memory allocation, data transfer, execution start, processing, interactions, and termination. Loading is when you start the application, the operating system finds the program's executable file in persistent storage. We have the memory allocation part, which is when the operating system reserves a memory space for the program, and we have data transfer, where the program's instructions and initial data are copied from storage to the allocated RAM. We also have execution startup. The CPU begins executing the program's first instruction from RAM. We have processing. The CPU alternates between fetching, decoding, and executing instructions while manipulating data from RAM. And we have interaction. The program can interact with other hardware components, for example, display, network card, etc., or request services from the operating system. And that's where the driver comes in. The driver handles the communication between computer components and the operating system, and we also have termination, which viruses obviously don't have. The program finishes its tasks and is closed by the user or the operating system. Its allocated RAM is then freed up for other programs. That's not the case with viruses. They never stop running. And we're going to do this in a hands-on lab in the future.
So, how does a CPU work internally, right? A CPU is a complex integrated circuit that contains millions, if not billions, of transistors, which are internal components that act as switches. So, we have the arithmetic logic unit, the ALU, which performs arithmetic and logical operations, obviously. We have the control unit, which manages the fetch, decode, and execute cycle, directing the data flow and coordinating operations. We have the registers, which are small and extremely fast memory locations inside the CPU itself. They hold the data and instructions that the CPU is currently working with. So we have other types of registers, program counter registers, which is the PC, instruction register IR. I'm not going to get into that right now. We're going to have a whole class on that, and it's a big one. We have cache memory inside the CPU, which are small, fast memory buffers located between the CPU and RAM. Cache stores frequently accessed data and instructions, significantly speeding up access time by reducing the need to go to the slower RAM. There are generally multiple levels of cache, L1, L2, L3, with L1 being the smallest and fastest. A website, for example, uses cache. So when I access a website, I don't need to go directly to the server's hard drive. I access it from cache. But what is cache actually for? Cache holds data that doesn't change frequently. It changes from time to time. So why would I need to access the hard drive, which is more costly, if I can access it from RAM instead? This reduces cost, reduces energy consumption, and the environment thanks you for it. The reasoning, the hierarchical nature of memory between registers, cache, RAM, and storage is a design trade-off. So we have a concept called reasoning. Yeah, speed comes at a cost in capacity and price. The CPU is designed to take advantage of this hierarchy, keeping the most immediately needed information in the faster memory layers. In short, that's what I talked about earlier. There's cache memory to reduce the access cost, which uses less energy, and this is a concept. It's a design. It's a concept called reasoning. All right, now let's talk about memory hierarchy and addressing. RAM is organized as a linear array of memory locations, each with a unique address. When the CPU needs to access data or instructions, it specifies the address to the memory controller, and the memory controller then retrieves the data from that specific location. Example, think of a RAM as a street with houses. Each house has a unique address. The CPU needs to know the address to get to a specific house and retrieve its contents, which are the data or instructions. So this addressing scheme allows the CPU to precisely locate and access any data or instruction in memory. Memory management units, which are called MMUs inside the CPU or chipset, handle the translation of virtual memory addresses used by programs into physical addresses, providing isolation and protection between different running processes. In other words, each cell has its own memory. Each memory has its own physical address, and this is done to avoid collisions, because multiple programs can be running at the same time, so each one has to have its own address, and they're kept isolated so there's no conflict between operations. Now, as for storage technology, I've already talked about HDDs and SSDs, so let me go over the difference between them. Choosing between an HDD and SSD involves a trade-off between cost per gigabyte. HDDs are cheaper and performance. SSDs are faster. For operating systems and frequently accessed applications, SSDs offer a dramatically better user experience, but they cost more. For example, I have a ton of data here at home that I save on hard disk drives. I don't need to buy an SSD just to access that data quickly. They're way more expensive. So I just buy a hard drive, make sure to store it somewhere safe, lock it up tight depending on what's on it, and that's that. Plus, a hard drive is easier to destroy, if you know what I mean. So if you've got sensitive data that could compromise your freedom, I'd recommend going with a hard disk drive. Now, if you want speed and to access your data faster all the time, I'd go with an SSD. Well, there's a lot more content on this over at zerosday.com. I'll drop the link in the description so you can read up on what this video didn't cover, all right? There's a lot more to it, and for this more conceptual and advanced part, I ask that you read it. To become a hacker or an IT professional, a cybersecurity professional, a programmer, a network analyst, whatever it may be, you need to learn how to read and you need to learn how to be self-taught. And I think that's the bare minimum, because you're going to have to write reports, you're going to need help, and a lot of the time your colleagues won't have the time to help you, or won't want to help you, or won't be able to help you, and then you'll have to read through documentation, and that's just life. Part of life is figuring things out on your own, and especially if you want to be a hacker. If you want to be a hacker, you absolutely need to know how to be self-taught. You have to build that culture of being self-taught, all right? So if you liked it, give the video a like, share it, all that good stuff. I'll put the link in the description that you'll need to read the rest of it, the continuation of this chapter, and even the upcoming chapters. Remember, if you want to donate any amount to help keep the platform running, since I don't make anything from keeping it up, click this Stripe link and donate 10 cents, $1, $5, whatever your heart tells you. See you next time.